All right. Uh, Hello, everyone, either watching live or watching on YouTube. Thanks for putting up with the fact that I'm going to be gone for the first week of class. So the first two lectures are going to be online as I stated on Canvas. So lecture one, introduction to this energy and transportation modeling class. We'll talk about some course logistics and then dive right into some of the first topics of the course. Okay, starting off, uh, office hours. So I will be having regular office hours once I come back. So these will be starting from January 16th, the second week of class. It'll be Tuesdays, 1 to 2 p.m. At my office at the EP Center. And if this specific time doesn't work for you, you're always welcome to reach out to me by email. And then we have Elizabeth as our TA for the course. She has not yet let me know about office hours, but I will post those as soon as she does. And her email is here as well. Okay, grading, you can find all of this information in the syllabus, but I'll go over it really quickly. So class participation, counting both attendance and participation, just 20%. And then the bulk of the grading in the class is going to be on your homeworks and final projects. There's going to be a total of 4 homeworks. And there's a 10% penalty per day. And then lastly, the final project is going to be divided into 3 pieces: a project proposal, final presentation, and then the project report. So I'll talk a little bit more about the final project, and we will a little bit later on in the quarter give a little bit more details and logistics, but generally what the final project is groups of 2 to 3. And then the components, as I mentioned, project proposal, that'll be due mid-February, 1 to 2 page proposal. The class presentations is going to be happening at the end of the quarter. So that'll be an in-class 10 to 15-minute presentation of your analysis. And then the project report is due at the very end of finals week. So I put 8 to 10 page paper, but length is sort of less important than content, right? And obviously the expectations are going to be different if you're doing like by yourself or if you have a group of 3 people. And the rubrics will be provided for each of these components. They're actually already posted on Canvas, so you should be able to find those already. Okay. And as I'm, this is usually where I get a number of questions. And since we're doing this online, you can feel free to, post your questions to Canvas and I can answer them so that everyone can see them as well. Okay, so let's dive right into it. Introductory concepts about the course. So thinking about systems modeling. So what is an energy system? The Intergovernmental Panel on Climate Change. This is one of the sort of large research bodies on climate change in the world, spans sort of many institutions and many countries. So they kind of describe this as basically all components related to production, conversion, delivery, and use of energy. And so more specifically, the goal of this type of modeling is to understand energy consumption and the impacts of that particular system. We'll find that the energy systems that we're looking at can vary in scope and size, right? And this depends on the context of the work that you're interested in. So some of the key issues that people try to investigate using these sort of energy models can include things like technology adoption, fuel consumption, cost and price, right? So thinking about economics of the system, and then emissions. So that can be either your greenhouse gas emissions, right, affecting sort of climate change level of activities, or it could be for criteria pollutant emissions, right, thinking about impacts on air quality. And the sort of interesting thing about energy systems modeling is that this is oftentimes a highly interdisciplinary subject, right? And so this is something that can span energy, engineering, environment, economics, also social and behavioral research. And so by spanning sort of many of these disciplines, you're getting sort of a better holistic picture of some of these key impacts. So to break this down in a little bit more specificity, general architecture of your energy system. So we typically think of the energy system in sort of these chunks. Primary energy, secondary energy, you've got your final energy consumption. And so primary energy, we'll give sort of more formal definitions a little bit later on in the slides, but primary energy you can think of as essentially resources that are coming sort of directly from nature, right? And so these are things that haven't been refined in any particular way or transformed in any way. And then secondary energy is when it goes through a sort of transformation process, right? So you can look at some of the components of primary energy, the raw fuels such as coal, oil, natural gas, the sun, wind, and how eventually these things get transformed to secondary energy, right? So electricity typically comes from, right, combustion of fossil fuels, spinning a turbine to produce electricity, or, you know, sunlight hitting a PV system to knock off electrons to go into your circuit, right? Or you have gasoline, which is refined oil, and so on and so forth. These secondary energy components go into feeding your sort of final energy consumption. And these are typically broken down into like sectors. If you think about those Sankey diagrams, some of which we'll look at in a bit, going to residential, commercial, industrial, transportation sectors, or they think even more specifically about the final energy going into specific technologies. And so that can be, you know, at the residential level, things like your appliances, your computers, your lights, and so on and so forth. And the last sort of box here are the services that you are actually providing. So the idea, and oftentimes this can be, the services box can be sort of left out, but it's an important consideration to remember, because the thing that we actually want isn't like the electricity or the gasoline, right? It is the actual service that those energies are providing. And it's an important perspective to keep in mind. So being able to move from point A to point B, getting lighting, getting heating and cooling, and so on. So those are the sort of end demand products of this whole sort of energy system. And to the extent where you are concerned about specific services, right, that's how you sort of inject, sort of work on that end upstream to the rest of the energy system, is to make sure that you include those in your schema. So it gets a little bit more detailed, right? In each sort of step, there is a whole bunch of other stuff that happens that can be included in your energy system, again, depending on the context of what you're investigating, right? But to get from primary energy to secondary energy, you might have extraction and treatment processes in order to get at the primary energy, and then conversion in order to transform your primary energy to secondary energy, right? And so this could be the operation of like power plants, the operation of your refineries. And so that whole transformation process is captured within the arrow from primary energy to secondary energy. Likewise, going from secondary energy into your final energy consumption, the distribution system of how I get my electricity from a certain point to your final energy consumption point, or other types of secondary energy, like fuels, for example, getting your gasoline from refineries to the gas stations where you're actually pumping and getting them into your vehicles, right? And so this whole system itself is a piece of the architecture that could play a role, again, depending on if that is part of what you're investigating. And so the application of these models, again, going back to those outputs and impacts that we're interested in, thinking about these pieces, and the 5 here that I'm showing is just a sort of subset of possible outputs, right? But these are sort of the more common ones that you see in this research. And the piece to not forget, particularly in this class, right, where we're talking about the application of these for policy, is sort of the interaction between the outcomes and even the creation and inputs of the models themselves with real world policy. And so that's going to come much more at the latter half of the class. We will talk about how you can interact and opportunities to inject sort of research discourse into the policy process. And we'll see some examples of these sort of larger scale system models and the impact that they've had on real world policies. So thinking about informing policy, what's the impact of, let's say, a specific policy change to a system? One of the best ways to sort of analyze that type of hypothetical outcome is through these sort of system models. And so this is informing policy creation sort of at the front end to understand, hey, if I want to pass policy A or policy B, you know, what sorts of outcomes are going to result from that? That could be sort of on the economic side of things, looking at cost implications, could be thinking about changes in emissions, right? Specifically or particularly if you are trying to target like a specific emissions outcome, this is one way to leverage a system model to look at what would happen essentially in the future. And it's a two-way street. So how can we use our knowledge and models to create good policy? So in that sense, You could be finding outcomes from your system models that then you think might make a sort of good policy, and that could lay the foundation for either legislation or regulation to be created. Okay, and so overview of the whole course. We're going to be talking first about background, building knowledge on your basic engineering and technologies. We'll be talking about tools, what analytical methods there are to develop some of the larger scale modeling systems, and what tools are commonly used in developing those modeling systems. We're going to look at essentially how to create these models from the tools that we learn about, and provide an overview of current day systems models, both in energy and transportation. And lastly, as I mentioned, the injection of policy discourse, where the models are applied, and understanding how how the models have informed real world policy decisions. So going back to this sort of architecture slide, right? The first piece of it is really sort of understanding the components of the technologies here, and the fuels. So we're going to talk about all of these individual sort of bullet points, and some of the processes in, extraction, treatment, conversion. And then we're going to talk about the construction of the system using specific tools. So once you have your general background knowledge about the technologies, and you are interested in specific types of outcomes, what tools can we use or are commonly used to do that type of analysis? And then we're going to look at the models holistically. Okay, so to begin, we're going to go all the way back to basics. Quick physics recap, to make sure that everyone is on the same page here. This is likely a review for some of you, but hopefully the perspective will still be somewhat useful. So what is energy? We are talking about an energy modeling course, so we want to make sure that everyone, again, is on the same page here. So energy is the ability to perform work or to heat an object. There are a whole bunch of different types of energy listed here. So kinetic, chemical, heat, electrical, electromagnetic, elastic, nuclear, and gravitational. We are going to talk about most of these, although some of them are sort of less relevant for the types of modeling that we're going to be talking about. One concept I wanted to make sure we're fairly clear on: conservation of energy versus energy conservation. These are topics in sort of slightly different fields that might get a little bit confusing or sort of overlapped in some ways. And so just to straighten that out, so conservation of energy in a sort of physics perspective, this concept is the idea that you can't create or destroy energy. It's just converting from one form to another. And so as you go from any sort of form of energy to another, you never actually lose any energy. But in energy sort of sorry, from the sustainability concept, this is actually a little bit different. Energy conservation is thought of as a reduction in energy usage to prevent wasting energy. And so this is like service or activity reduction, which means that you just use less of it, or you're improving energy efficiency to decrease energy use. And so as I use some of these terms, just make sure to keep these straight in your mind, and I'll try and be conscious of what I'm talking about with respect to conservation of energy versus energy conservation here. Okay. How is energy measured? There are a bunch of different units of energy that are commonly used. And you may have seen some of these. So you've got joules, you've got watt hours, you've got BTUs, which stands for British thermal unit. You've also got calories, and then EV is electron volts. That's a unit of energy that's used at sort of the atomic level, which we're really not going to deal with in this class at all. But the other four may sort of pop up. So the first energy unit is the joule. This is probably the most common one, and hopefully one that everyone has seen before. This is kind of your gold standard for energy units. This is the international standard, or SI unit, for energy. And this is used across a very broad set of applications and fields. So the actual definition of a joule is the ability to heat 1 gram of water by 0.24 degrees Celsius at 1 atmosphere. And maybe the easier one to remember is the amount or the amount of energy used to move 1 kilogram a distance of 1 meter at 1 meter per second squared. And so again, the joule, as its sort of international standard, it's going to be one of the most common ones when we think about sort of anything pertaining to energy. However, because we talk about electricity quite a bit in this course, it'll be important to have a good grasp of watt hour as well. I'm actually gonna come back to this in a little bit, but I'll kind of quickly cover the sort of concept here. But it'll be maybe easier to understand once we get to power and we talk about watts. But for now, just know that this is most commonly used in electricity, and it is the amount of energy used at a constant power rate over a period of time. So you probably have heard of watts before, which is a unit of power. And energy is the equivalent of some wattage used over a specified amount of time. So a watt hour is simply equal to 3.6 kilojoules. So the last unit that we talked about, right, joules, it is 3,600 joules. And we'll see where that number comes from in a little bit. At the residential level, the consumption of electricity is most often measured in kilowatt hours. So you may have seen this picture, or I should probably use a more updated one with smart meters. But This is an electricity meter at your house that tells you essentially how much electricity that you're using. And you'll notice that the units is specifically in kilowatt hours. And that's, again, in a sort of easy way of measuring electricity consumption. Okay, British thermal units, commonly used to measure the energy content of fuels. So the amount of energy used to raise temperature of 1 pound of water by 1 degree Fahrenheit. So this is kind of like the imperial version of a joule, essentially. So 1 BTU is just a little bit more than 1,000 joules. So 1055 joules. And most commonly is used to describe the energy content of natural gas. MMBTU is something that you'll see used to describe this, and that just means 1 million BTU. And 1,000 cubic feet of natural gas is the energy equivalent of about 1 MMBTU, which is also about 1 gigajoule. There's another unit called therms, which can be used to describe energy content of natural gas as well. So 100,000 BTU is equal to a therm, so 10 therms to an MMBTU, and that's about 100 cubic feet of natural gas. The last one related to BTUs that's very common is known as a quad. So this is 10 to the 15th BTU or a quadrillion BTU, hence the quad. This is a very large quantity of energy, and the reason why it's used is to represent energy consumption at really large scale. So thinking about large scale economies. So when you're talking about the energy consumption of like a state or a country, or even like a continent, sometimes they'll use quads as opposed to your joule units. Okay, last one that I'll talk about with energy is calories. And so this one, I'm sure everyone has seen before, right? This is most typically used to measure the energy content of foods. So it is kind of like the metric version of the BTU. It's the energy required to raise the temperature of 1 gram of water by 1 degree Celsius at 1 atmosphere. So 1 calorie is equal to 4.2 joules. You'll remember that the joule is 0.24 grams of water by 1 degree Celsius, so 1 atmospheres. So smaller than a calorie. And the place that people most often interact with calories, right, are these sort of nutrition fact labels. But one thing to keep in mind here is that the calories on food labels are actually kilocalories. When we think about it in reference to this definition, energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So here on this nutrition label, it says it's 25 calories. It's really 25 kilocalories or 25,000 regular calories. So in this class, we're going to talk about energy all the time. And so if the concepts here are sort of less familiar to you, it's definitely something that you want to get comfortable thinking about. And so one thing that you guys can do, um, you can maybe pause the video and have a guess at what the energy content of each of these things are. You can do it on a order of magnitude basis. So the average meal is that. You can think about this in different types of energy units too, right? So the average meal, 1 to 10, 10 to 100, 100 to 1,000, joules or calories. And you can think about what it would be for each of the items that you see on this slide. So go ahead, take a second to guess what the numbers would be here, and we'll go through these pretty quickly. So the average meal, I think this one is maybe one of the more straightforward ones, right? Because you can think about, okay, I need, if you've heard of this before, like 2,000 calories a day, or 200 or 2,000 kilocalories a day, and what that would mean for one meal, right? You're probably thinking about 100 to 1,000 calories. Again, kilocalories, again, this is on the order of magnitude, which is equivalent to 100 to 1,000 kilojoules. The human body contains about 1,000 times more, so 100 to 1,000 megajoules. Let's say you get a big lump of coal for Christmas. That'll run you a nice 10 to 100 megajoules. Probably on the sort of lower end of that order of magnitude. Gallon of gas is going to be on the higher end of that. So a gallon of gas is usually around 100,000 BTUs, or about 100 megajoules. So it's nice to get familiar with some of these numbers, so that you can kind of quickly understand, for example, the energy content comparison between different fuels, right? And so does sunlight have more or less energy than these things, right? So if you were to try and capture energy of the sun on, let's say, 1 meter square of ground for an hour, on average, you're going to be on the order of 1 to 10 megajoules. Okay, for an EV battery, so this one is often described in terms of kilowatt hours. And so, with a sort of long range Tesla, for example, you're talking about on the order of something like 100 kilowatt hours, right? And so that's about 1,000 megajoules, order of magnitude, right? So you can think about the comparison of the EV battery with a gallon of gas, right? So 100 kilowatt hour battery, the energy content of that would be roughly the same as 10 gallons of gasoline. Okay, so how much energy does the average household use within a day? So 10 to 100 kilowatt hours. And then a nuclear bomb. So that is 10 to 100 petajoules, or that would be the equivalent of 10 to 100 billion megajoules. So if you compare this to household energy consumption, right? We could say that the energy in a nuclear bomb would power something like something on the order of 100 million to 1 billion houses per day, something like that. Oh no, sorry, 10. I got my units wrong. 10 million to 100 million houses for a whole day. Okay, how much energy does the entire country use? The annual consumption of the US is about 100 quats, which is about 100 exajoules. And the worldwide energy consumption is 100,000 terawatt hours. So order of magnitude 100 to 1,000 exajoules. And the US, right, sometimes they'll measure things in quads because we use imperial units, but most of the rest of the world is going to do something more like this, terawatt hours. And to give folks a sense of energy consumption by source and sector, this is your sort of primary energy on the left, and how much of each of these things go into your different sectors. You have your intermediate sort of electricity power sector here that you can see different fuels are going into, and your end use sector here. We see the total energy consumption. So this was in 2021. Across all of the US, 73.5 quadrillion BTU. And that gives you a sort of description of the energy of each of your sort of pieces of your energy system. All right. So the next piece that we'll talk about is power. So that is the rate of doing work. In other words, power is energy divided by time. So if you were to move an object from point A to point B, it requires some amount of energy to do it, but you could do it very quickly, which would take a lot of power, or you could do it really slowly, right, which would use a lot less power, but you would need to be exerting that power for sort of a longer period of time. So power is an important concept to describe the use of energy over time, which we measure as the sort of most commonly as watts, or in units of horsepower. So watts is the equivalent of joules for power, or it's analogous, right? It is the SI unit for power, and 1 joule is simply equal to 1 joule per second. So if you think back to the original slide with watt hours, that's where the 3.6 kilojoules comes from, because 1 watt hour is simply 1 joule per second over over the course of an entire hour, and there's 3,600 seconds in an hour, and so that's where that number comes from. So anytime you have a watt hour, that's just multiplying by an hour time, and so you are essentially going up 3,600 by a factor of 3,600 if you want to sort of interchange between the amount of energy used over that time period versus the power output. So again, very common to describe electricity. So for example, the capacity of a power plant. We talk about things like installed capacity of a power plant. That means that it can physically produce up to that amount of instantaneous power. So a 10 megawatt power plant can produce up to, but not more than 10 megawatts. And if I were to run that for 1 hour, the amount of energy that power plant would have produced would simply be 10 megawatt hours. And so again, the watt hour, kilowatt hour, megawatt hour unit makes the conversion between energy and power very easy. We do also talk about energy use in transportation. And so if you think about the context of horsepower, the most common context for horsepower, that's usually to describe the power of like an engine, sometimes even motors, so mechanical power. So the definition of a horsepower is that it can lift 75 kilograms, 1 meter in 1 second. So thinking about watts, it does get, unfortunately, a little bit confusing. There is actually an imperial horsepower and a metric horsepower, which are ever so slightly different. So 745 watts versus 735 watts. And if you think about where this comes from, so think about how much power, how much horsepower a single horse can provide. And it's actually a little bit less intuitive. Actually, the peak power production of a horse is actually about 15 horsepower. Okay, again, similar type of thing. This is going to be a fairly important concept in this class. So trying to get a good handle on power. We can do maybe the same exercise here. Go ahead and pause the video and see if you can guess what the power rate would be for each of these things, either power use or power consumption or power production. So for a light bulb, that's going to be 10 to 100 watts. Although I keep forgetting to update this. Sort of more modern day, you're probably talking more about 1 to 10 watts instead of 10 to 100 watts. And so, a decade or maybe even 15 years ago, we would be talking more about incandescent light bulbs, which would be 50, 75, 100, 150 watts. And that has really come down in power consumption, thanks to first CFLs and then to LEDs. Now you're talking about producing the same amount of end service, right? So the light for a small fraction of the energy consumption. So these days, it would be a much better answer to say 1 to 10 watts instead of 10 to 100 watts. Okay, exercising human, you are typically going to be using about 50 to 150 watts of power to do things. Again, depends on the activity, right? But if you are running or biking, you might be sort of on the upper end of this versus being more relaxed, like walking. So microwaves, these guys use quite a bit more power, but they are used for a much smaller amount of time. And so microwaves, you're typically talking about on the order of a kilowatt or so, or 1,000 watts. Solar panels, so if you are talking about, sort of a single panel, you might see these things on your common rooftop. You might be on the order of about 300-ish watts for a panel. But you've also seen, these solar, we'll call them sort of solar plants, right? These are known as sort of utility scale solar. That you might see installed over these vast swaths of like desert land in California, for example. And the size of these plants can be anywhere from 100 to 1,000 megawatts. The average household uses about 1 kilowatt of electricity. Again, there's a lot of variance here, but on average, it's about one kilowatt in the US. Easy number to remember. Your typical engine. So this is anywhere between 100 to 1,000 horsepower. And order of magnitude, it's going to be similar, 100 to 1,000 kilowatts. Wind turbines. So this is typical size of a wind turbine. You might be somewhere between 1 to 3 megawatts, actually sometimes even bigger these days, especially for the large sort of offshore wind turbines. And again, we'll talk a little bit more in detail about these things once we get to that specific technology. But wind farms are getting quite big these days. You're talking about on the order of 100 up to even a gigawatt in size for wind farms. The natural gas plants, 10 to 1,000 megawatts, large variance in size as well. Next up, your coal plants. These tend to be on average a little bit bigger. Again, these are order of magnitude. The largest sort of coal plants in the US can be several gigawatts. And I think the largest ones in China can be bordering, 10, approaching 10 gigawatts. I don't know if there's actually any coal plants that big, but order of magnitude, you're talking about a little bit bigger than natural gas plants on average. Your nuclear plants are typically not going to be any smaller than a gigawatt, but they'll reach kind of the same sort of ceiling and sizes as your sort of large coal plants. Okay, power consumption for all of California. So peak power, maybe on the order of 50-ish gigawatts. So this would be approaching kind of the capacity of power production in the States. This is not the average this is not the average sort of power consumption of the state. Would be on like the hottest day when everyone's got their AC running and they start having those alerts about turning off your power. You're on the order of about 50 gigawatts. Across the whole world, the total installed capacity of basically all of the power plants across the whole world is about 15,000 gigawatts. So that'll hopefully give some sense of size and scale of the sort of total power plants that are installed across the entire world. Okay, So that kind of wraps up concepts of energy and power. So the next thing to talk about is energy efficiency, and I should probably add energy through conversion as well. So energy efficiency tries to reduce the amount of energy required to provide products and services. That is the concept of of sustainability when you want to improve efficiency. But the other thing to note, right, is that any process, any conversion process, we are going to lose useful energy in some sense. So again, from the perspective of conservation of energy, you're not actually losing any energy, but there's a concept of known as exergy, which is talking about kind of the conversion or the conservation of useful energy. And typically what's going to happen is that anytime you do a energy conversion process, in other words, anytime there's an arrow in this original sort of diagram, you are going to lose energy to heat, or you're going to lose useful energy to heat. And so the efficiency is also talking about kind of the concept of what you retain in usefulness as you convert between sort of materials and energy. So this is actually going to conflate again with a sort of physics topic. So when we think about efficiency versus efficacy, which is like the strictly correct nomenclature for the concept that we're going to be talking about today and sort of onwards the rest of the class. So energy efficiency, strictly speaking, is a dimensionless number, and it's always less than 1. So the units of the numerator are the same as the units of your denominator. So you have some work or energy output divided by energy input. And again, this is always going to be less than 1. Well, the concept that we're going to be working with in this class is actually better known as efficacy, but kind of for common nomenclature sense, we're just going to be calling this efficiency. So when we think about efficacy, this is similarly as energy efficiency, you have this ratio of output to input, even if they don't have the same units. So if you think about like the efficiency of a car, for example, that's in units of miles per gallon, or for a light bulb, lumens per watt. Again, this is efficacy, but we're going to use this kind of interchangeably with the term efficiency. And so efficacy is just your service output divided by your energy input. And the reason why physically, if I confine this to sort of a sort of more physics-based efficiency term, efficacy makes it starts to become a little bit less intuitive. I have this, if anyone's heard of XKCD, they do kind of these interesting explanations of these things. So for example, miles per gallon, if you think about this conceptually, miles is a unit of length, gallon is a unit of volume. So you would end up actually with something like miles per gallon would actually be something like 1/meter². And it actually describes like the cross-sectional area of like a string of gasoline across the miles that it would go in that sort of actual MPG term. You can read about it for some kicks and giggles. Okay, so thinking about efficacy, which we're going to just talk about as efficiency. So work or energy output divided by energy input. So in this case, you could convert these things to the same units, right? And so my input is 100 kilograms of corn and my output is 11 gallons of ethanol. You could just say that it would then be 0.11 gallons of ethanol per kilogram of corn, or you can convert it to like a thermal efficiency sense, right, by going to energy. And so if we know the energy content of 100 kilograms of corn is 18 megajoules per kilogram, or 1800 megajoules, and the output is 11 gallons of ethanol, which has an energy content of 89 megajoules per gallon, then you would have 979 megajoules of output. And so the efficiency of this process would be 54% efficient. In other words, some of the energy content of your corn is lost as it produces your ultimate output of ethanol. And most of that energy is typically lost to things like heat or other sort of byproducts that you won't be able to capture that energy. But again, it doesn't have to be in those units, right? So in this case, what is the efficiency of like this pipeline? Let's say you have 100 gallons of fuel going into it and you only get 95 gallons out of it. Efficiency is just 95 over 100, so 95% efficient. Similarly speaking, another sort of example of a thermal efficiency that we could be talking about here. You could do it by work or power input and output as well. So if you have 60 watts of electricity inputs, right, and then you have a 3.1 watt energy output, so this would be common for example, for an old incandescent light bulb, right? You can see that the efficiency of this light bulb is only 6%, so 3.1 divided by 60. And that seems super low, which it is. And if you recall, holding your hand close to an incandescent light bulb, it's really hot, right? And so most of, or I would say all the remaining energy that had been input is actually lost as heat. And only a small portion of that is resulting in sort of light energy, which is the thing that you actually want. And so you can have technology improvements, right, to improve things like efficiency. One of the common examples of this that people point to is the refrigerator. This is kind of the golden success story of energy efficiency for a couple of reasons. You can actually see that this was one of the areas where you could get your really good bang for the buck, right? For refrigerators, if you look at trends over time for this technology, in the blue line, you can see that it's getting a little bit bigger over time. Fridges get slightly bigger, but at the same time, the energy consumption was decreasing and it was getting cheaper. This is a very unusual type of trend, right? Usually you're trying to make a trade-off for energy efficiency that typically increases things like the price or decreases some other performance attribute that you might care about. So to the extent possible, you would companies and individuals would always want this type of outcome where you can always take advantage of the sort of low-hanging fruit and be able to get things cheaper and more energy efficient. But it's not always the case that you can have these types of trends in your technologies. Okay, energy pathways. So this is related to the sort of conversion aspects of efficiency, but as I mentioned before, the definitions of these things. So primary energy are naturally occurring resources. So crude oil, natural gas, coal, sunlight, wind, geothermal, and tidal energy. These are all examples of things that are sort of available without any conversion or refining processes. Primary energy can then be processed into secondary energy. So these are resources that are converted or modified to become an energy carrier. So things like electricity or hydrogen. And for fuels, things like refined liquids such as gasoline or processed natural gas. And final delivered energy, these are energy carriers or fuels used in final energy appliances to provide your services. So this is like the electricity arriving at your house or the gasoline at the gas station. And these are then converted to the energy service that you ultimately care about. Okay, so energy pathways. So as I go from primary, secondary to final energy and so on, you'll note that you have sort of these losses happening. And the amount of loss is directly attributable to sort of the efficiency of your conversion systems. And as you can see, your primary energy is always going to be larger than your secondary energy, which is always going to be larger than your, final energy consumption stage. So one concept to think about is, as we think about energy efficiency and improvements in energy efficiency, right? There are many points within your energy system where you can improve it, right? And so should we be thinking about improving energy efficiency at the final service stage, right? So improving the light bulb, or should we be making your, for example, power plants more efficient? So improving the efficiency from your left side to primary energy to secondary energy. And there's not always a sort of straightforward and clear answer, right? So if you do improvements in your final to service efficiency, one of the big benefits is that it reduces the amount of energy needed at each upstream stage. And you have sort of less mining and oil extraction, fewer power plants, fewer pipelines, and energy losses all along that entire supply chain. And we're going to look at an example of this that hopefully will make this a little bit more clear in your minds. We'll end on that. But you can also do improvements to the primary to secondary efficiency, even though you don't get the benefits at all the upstream stages. One of the things is that it can be much easier to implement, right? So essentially implemented. So if you think about improving like a coal plant, then you're talking more about like corporations who typically act more like rational actors. It might be easier to improve a power plant, a single power plant, rather than hundreds or thousands or millions of individual consumers. So one thing to keep in mind is sort of the trade-offs between these two. So calculating efficiencies. So the efficiency of a system or the life cycle of that system can be measured by the individual efficiencies of each process. So the energy efficiencies are multiplicative. Don't worry too much about this nomenclature here. I'll show an example in just a second of what this is referring to. It really just means that the efficiency of your pathway is equal to the product of your efficiencies, right? So this giant pi is the equivalent of your summation, but for multiplying, for multiplication of objects. So we'll see what that, how to use that in this next example. So example of life cycle energy efficiencies. So these are all examples of going from your primary energy to your useful energy. So one for coal, one for natural gas, and one for conventional raw crude. So for coal, it has to go through a coal processing step. It gets input into a electric plant, and then it gets converted to electricity, which is your secondary in blue. And then that gets passed on to a manufacturing plant. And you can see in each stage, it describes the input amount of energy and the corresponding amount that you get after that specific process. And we can see this happening for all of these stages. So natural gas going to a refinery, eventually getting converted into electricity, and so on and so forth. If you look at the input versus output size, it gives you some indication, right, of where you're getting the most energy losses, right? So from here to coal processing, you lose 0.01 exajoules. From here to here, you lose 0.1 exajoules. But then from coal to electricity, you're losing 0.71 exajoules. So quite a bit larger loss than the previous ones, right? And so we can actually calculate this, as I was mentioning before, right? Efficiency is just your output over your input energy. And so to calculate the efficiency of any individual process, I could just apply this equation. So 0.99 divided by 1. So this process is 99% efficient. 0.89 divided by 0.99, that's about 90% efficient. The step where we lose the most amount of electricity is only about 30% efficient. And then the rest of them are a little bit more efficient, right? So close to 90% and 70%. And so you can get from your start to your finish and look at the overall pathway efficiency by just doing the energy output divided by the energy input. In this case is 18%. And the point of the equation from before is just to demonstrate that actually that 18% is also equivalent to if I were to multiply all of these efficiencies together of each of my process steps. So 1 times 0.99 times 0.899 times 0.315 times 0.893 times 0.72. That will also get you to your 18% efficiency number. And so this can be useful to understand the aggregation of various steps of your whole process. Like if you only wanted to go from one box to let's say from box 4 to box 5, you could do a similar type of thing here. So efficiencies are multiplicative to get at sort of the system level efficiencies. We can do this for vehicles as well, right? So this is a gas car versus an electric car. You can think about the life cycle of these vehicles and what the relative efficiencies are. So here we can see in the first row, conversion of oil to gasoline. The refining doesn't lose too much energy, but the big step where you lose the most is from the actual use within the combustion engine vehicle. Tends to be not very efficient. You can compare that to electric vehicle efficiency, which is much higher. But you can think about how that compares across the whole sort of life cycle as well, right? And so if we wanted to view different components of the energy consumption and conversion process, you can look at the sort of whole life cycle according to the table here. Okay. The last thing we'll talk about is this concept. Oh, let me jump back really quick. This concept of conversions, improvements in final to service versus primary to secondary. So we're going to look at across the sort of life cycle system for efficiency, what happens if I improve different pieces of the system. Okay, so we're going to start with this example here. This shows the thermal power, energy, and losses to produce light from a light bulb. So starting with my primary energy, it says here I have 320 units of primary energy, of which are needed to produce 112 units of electricity. And that is a fairly inefficient process. So you lose about 65% of the energy by combusting your fossil fuel. And then that electricity has to get sent through your electricity system, your transmission system, distribution. You have some losses happening there, 5% in each case, followed by wiring, a little bit of losses, and then your customer lamp This might be an inefficient incandescent light bulb, right, that we were talking about, where most of that energy is lost as heat. And then you get your 1 unit of useful light, right? And so this pathway is describing kind of a ratio of 1 to 320. So 1 end service unit divided by 320 input units of energy. And so let's think about what would happen if I were to improve the light bulb efficiency. So this piece right here, versus if I were to improve the upstream power plants. So this slide shows 2 examples. So the first one is where I improve the power plant efficiency. So we can see, and I get the same amount of electricity here. So 112 units of energy coming out of generation. So that is the same as our previous slide here. But instead of 320 units of input, because the power plant itself is more efficient, I only need 224 units here. And so if I go from 320 to 224, that's about a 30% reduction in primary energy to reduce my same end goal 1 unit of useful light. So you're actually getting a sort of fairly good, right, improvements and reduction in energy requirements to get that same outcome. However, let's say you did a slight improvement to your light bulb, going from a 2% efficiency light bulb to a 10% efficiency light bulb. So this is a 8% gain as opposed to a 15% gain up here. We can see what happens. So instead of 100 units here, you'd only need 20 units, right? Because it's 10% efficient. And if we trace back to the same losses and efficiencies through the rest of the process, you can see the primary use is only 64. So a much larger reduction in primary energy. And so looking at this specific slide, we can say, hey, it would make a lot more sense to simply make your end service much more efficient as opposed to your first primary piece. But again, going back to the slide from earlier, this does seem better in reducing the energy needed in your upstream stage, but again, implementation might be a lot easier for something like a power plant improvement. All right. I kind of flew through my slides since there aren't any sort of regular class asking questions. So that's actually where I'm going to end today. So we'll have a slightly faster video to watch. But again, in the case where there are any questions, do feel free to post those online. And maybe we'll spend some of our first in-person class to answer any questions as well. So with that, that'll be the end of our first lecture. And yeah, make sure to get through the second lecture as well before our first in-person class meeting on January 18th.